Hello and welcome to a lesson on solving logarithmic equations. So let's have a look at this warm-up first. So see if you can figure out how you would find the value of log to the base 3 of 10, knowing that 2 to the exponent of a is equal to 5 and 2 to the exponent of b is equal to 3. Okay, so take some time to try to express log to the base 3 of 10 in terms of a and b. Now this problem does require a similar technique to what was on the last quiz. So the first thinking question from the last quiz. So make sure you refer to that if you're not sure about what you would do, how you would start off this, how you would approach this problem. Okay, so I would recommend pausing the video and attempting to figure this out. Okay, so assuming that you have attempted this warm-up or have figured it out, let's have a look at how we would approach it. So we're given 2 to the exponent of a is equal to 5 and 2 to the exponent of b is equal to 3. We're asked to find the value of log to the base 3 of 10 in terms of a and b. So the first thing that you could do is you could rewrite each in logarithmic form. So we would have log to the base 2 of 5 is equal to a, and log to the base 2 of b, or not b, sorry, 3, is equal to b. Now, we want to write the log to the base 3 of 10. We want to write it as log to the base 3 of 5 multiplied by 2. Okay, so we want to decompose the 10. And then we want to use the product law and write this as log to the base 3 of 5 plus log to the base 3 of 2. Now the next step is kind of tricky. We want to replace the 5 in log to the base 3 of 5 with 2a, because that's what 5 is equal to, plus log to the base 3 of 2. Now we can bring the a in front by using the power law. So a log to the base 3 of 2. Now notice that log to the base 3 of 2 and this equation here, so log to the base 2 of 3 is equal to b. What we can actually do with this is if we use the change of base formula and we switch the base and the argument, so we actually make this log to the base 3 of 2, then the right side changes to 1 over b. Okay, so basically what we're doing is we're changing the log to the base 2 of 3 to log 3 over log 2. We're reciprocating to get log 2 over log 3. And when we reciprocate, we also have to reciprocate the right side as well. So b ends up becoming 1 over b. So that means that log to the base 3 of 2 is equal to 1 over b. Now, we already have this log of 3 to the base, log to the base 3 of 2 here as well. Then we can change it here as well. So we can write it as a multiplied by 1 over b plus 1 over b. So that ends up being a over b plus 1 over b. So that would equal a plus 1 over b. Okay, and so this is actually one of the questions in the textbook. This is a textbook question. So it is also a math contest question. And that's why it is somewhat difficult and does require some thinking and thinking outside the box. But yeah, so in terms of a and b, log to the base 3 of 10 is equal to a plus 1 over b. Okay, so let's recap a few things. So the definition and laws of logarithms can be used to solve equations that contain logs. Recall that y is equal to log to the base b of x has the restrictions b it has to be greater than 1. Y belongs to a set of real numbers, and x has to be greater than 0. It is important to remember that y is equal to log to the base a of x is defined only for x is greater than 0. Some equations will give roots that are less than 0. The roots must be checked in the original equation to see if for y is equal to log to the base a of x, x is greater than 0. If not, these roots are extraneous, so we basically exclude them. All right, so let's have a look at some examples of simple logarithmic equations, and we're going to try to solve them. So log to the base 6 of x minus 5 is equal to 2. So in order to solve this equation, we would want to convert it to exponential form. So we would have 6 squared is equal to x minus 5. And then we would just have 36 plus 5 actually is equal to x. So 41 is equal to x. Okay, so that one's pretty simple. Now this one over here, there is a base of 10 here. So we can write this as, I'll just write it as x squared minus 21x. Root of that is equal to 10 to the exponent of 2 over 5. And yeah, this is a fifth root. So this can also be written as x squared minus 21x to the exponent of 1 over 5 is equal to 2 to the so is equal to 2 over 5, 10 to the 2 over 5. And what we can do now is we can raise both sides to the exponent of 5. And that would give us x squared minus 21x is equal to 10 squared. Okay, so we're basically multiplying the exponents by 5. We get x squared minus 21x minus 100 is equal to 0. This is factorable. It's x minus 25 times x plus 4 is equal to 0. And then we just solve for the roots. X is equal to 25. And x is equal to negative 4 would be our two solutions. All right, looking at example 3 now. We would want to use the product law. So we would get log to the base 6 of x plus 3 multiplied by x minus 2. That's going to equal 1. Now we would want to convert to exponential form. Now you could also expand first. So this is just 6 to the 1, or 6. We can expand now and get x squared. So this is going to be plus 3x minus 2x. So that's just going to be plus x minus 6 is equal to 6. Moving the 6 from the right side to the left side, we're going to get negative 12. So x squared minus x minus 12 equals 0, which factors to x minus 4 multiplied by x plus 3. That's going to equal 0. And then solving for the roots, x is equal to 4 and x is equal to negative 3 would be our solutions. Now, this is where restrictions come into play, and we have to consider them. Now, for the previous one, we probably should have also considered restrictions. But let's first do the restrictions for this. So, if we look at what we have originally, and we want to look at this, we can see that it's okay if x is 4. There's no issues here, because our argument is still going to be more than 0. However, if x is negative 3, this is going to be undefined. And also this is going to be undefined, because log to the base 6 of 0 is undefined. So we would have to exclude x to the exponent of... we're going to have to exclude x is equal to negative 3 here. And so our solution is just x is equal to 4. Now let's go back here and just see if both of these are fine. So for the first one, for example 1, 41 is fine, right? Because 41, if we substitute back into the equation, 41 minus 5 is going to give us a value that is greater than 0, right? It's going to give us 36, and that's fine. So that works. Now looking at example 2 for the restrictions, we can't have a negative. We also need something that's greater than 0. So if we try to figure out what they are, we would actually have to take the x squared minus 21x, and we would have to set it to be greater than 0. We want to solve this inequality. So x times x minus 21 greater than 0. We can use a number line here. So assuming we have 0 and 21, and this is a quadratic. So we're solving this by graphing. So it's positive here, negative here, positive here. So we want it to be positive, right? So we have a value that's less than 0, which is fine here, and a value that's more than 25. So they both check out. They're both good. Okay, so they are both solutions. Okay, let's look at example 4 as well. So now we're going to be using the quotient law of logarithms. So log to the base 5 of x minus log to the base 5 of x minus 1 is equal to 1. Log to the base 5 of, so this is going to be x over x minus 1 is equal to 1. So quotient law. And then this is going to turn into x over x minus 1 is equal to 5 to the exponent of 1. And then we multiply both sides by x minus 1. We get 5 times x minus 1. X is equal to 5x minus 5. Move the 5x to the right side. We get negative 4x is equal to negative 5. And then we can divide both sides by negative 4. We get 5 over 4 as our final answer. Okay, and so we can check this though as well, just to make sure that it doesn't result in an undefined log. So we substitute 5 over 4 here, it's fine because 5 over 4 is greater than 0. And then if we substitute 5 over 4 here, it's also okay because 5 over 4 minus 1 is greater than 0. So then this is fine. This would be a solution to this equation. Okay, so let's have a look at some practice problems. So these are similar to the examples. So I would recommend pausing this video and trying to do these questions first, and then pausing the video to see the solutions. All right, so here what we would want to do for part A is we want to use the power law and bring the 2 on top. Log to the exponent of 4, log to the base 4 of 4x plus 3 equals negative 1. Now, since there's a subtraction between the logs, we can use the quotient law. So log to the base 4 of x squared over 4x plus 3 is equal to negative 1. And now we have x squared over 4x plus 3 is going to equal 4 to the negative 1. So we are converting to exponential form now from logarithmic form. This is going to end up becoming, going to look a little strange. So x squared is going to equal, so we would want to change the 4 to the negative 1 to 1 over 4. So if we do that, we're going to have 1 over 4 times 4x plus 3. X squared is equal to x plus 3 over 4. Which means we have to multiply everything by 4 to get rid of the fraction. So 4x squared is equal to 4x plus 3. 4x squared minus 4x minus 3 equals 0. Now we have to see if we can solve this by factoring. And it does appear that I think we can, because there are two numbers that multiply to negative 12 and add up to negative 4. So just have to see now. So let's see, 2 and if we go with 2 and 2 and 3 and 1, let's see, this should work. So this is going to be negative. Yeah. Okay, so it is factorable. So 2x plus 1 times 2x minus 3 is equal to 0. So yeah, crisscross does work. So x is going to equal negative 1 over 2, and x is going to equal positive 3 over 2. In terms of restrictions, x cannot equal negative a half because of this one here, this log here, we can't have a negative argument, right? So we would exclude that value. So 3 over 4 should be fine for both of them if we substitute 3 over 4, and it's going to give us a positive value. So we exclude the negative 1/2, so it's a extraneous root. All right. Part B. So logged, let's see here, log, there's a log on both sides here. So we would want to combine them first. So let's bring them together first. Log to the base 3 x squared over x plus 3. So quotient law. And what we can do with the logs is we can drop them. We have log to the base 3 on both sides. We can drop the logs, and we get x is equal to x squared over x plus 3. Multiply both sides by x plus 3. And then on the right side we have x squared. Expand x squared, it's going to be plus 2x minus 3 equals x squared. And this is ultimately going to end up becoming 2x minus 3 equals 0. If we move the x squared to the left or right. And then we end up with 2x equals 3, so x is going to equal 3 over 2. We do want to make sure that this is a valid root. So we go back to our original equation and look here. So if we put 3 over 2 in here, 3 over 2 minus 1 is 0.5, so that's fine, that works. Squaring it works, it's still greater than 0. Here it's also going to be greater than 0, 3 over 2 plus 3. So 3 over 2 is one of the roots, it's a solution. Well, it's the only solution here, actually. Okay. And then this last one here, algebraically determine all points of intersection of the two functions. Also sketch a graph of both functions to verify. So we're going to have to equate them to each other. We're going to have to set f of x and g of x equal to each other. And so that's going to look like this. We're going to have log to the base 2 of 2x minus 2 is going to equal 5 minus log to the base 2 of x minus 1. And so now we would want to move the log to the base 2 of x minus 1 to the right side. Going to be an addition. Equals 5. We can now use the product law. So log to the base 2 in this case of 2x minus 2 times x minus 1 is equal to 5. We're going to get 4, or actually not 4, 2. 2x squared. So minus 2x minus another 2x, negative 4x plus 2 is equal to 2 to the exponent of 5. So just changing to exponential form and expanding at the same time. So 2x squared minus 4x, it's going to be 2 minus 32. So minus 30 is equal to 0. Can factor out a 2 to get x squared minus 2x minus 15. That's equal to 0. And then this does factor. X minus 5 times x plus 3. That's equal to 0. X is equal to 5. X is equal to negative 3 here. To find the y values, we would substitute into one of the equations, right? So if we, let's say, let's go with f, seems simple enough. Or maybe even, yeah, let's go with f, it doesn't matter. F at 5 would equal log to the base 2, and then if we put 5 in, so 10, so 2 times 5, 10, minus 2, 8. So we know that that's equal to 3. And then if we put negative 3 in, if that even makes sense here, that shouldn't. That wouldn't make any sense. So yeah, we can't find that. So that's undefined. Just telling us that there's going to be only one point of intersection, not two. So equals an undefined value. So okay, so if we try to graph this, we know we have a point of intersection at 3 and 5. Okay, so point of intersection at 3 and 5. So that would be here. This is what we're expecting. So f of x, let's see how we would graph this. So it's log to the base 2 of 2 times x minus 1. So it has been translated to the right. The vertical asymptote is now at x is equal to 1. What we also know about it is it's being compressed by a factor of a half, right? So to help us, what we could do is we could take the base points of it and apply the mapping notation. So in this case, it's going to be x plus 1 over 2, actually. So times a half. A half times x plus 1. And then the y's don't change. Y stay the same. So our original points that we can go with for this could be 1. So 1 and 0. 2 and so base function here is log to the base 2 of x. So if x is 2, then we have a y value of 1. If x is 4, we have a y value of 2. If x is 8, we have a y value of 3. So that should be enough. We don't really need more points than that. So we're transforming these points. So 1/2 times 1, a half. So that's 1.5 and 0, 2 and 1, 3 and 2, 5, and 3. So 5 and 3 is that, okay, so what is our solution here? 5 and 3. Oh, I didn't plot 5 and 3 correctly then. Now I'm realizing it. Yeah, so 5 and 3, yeah, it's here. 5 and 3. Okay, so let's try graphing this. 1.5 and 0. 2 and 1. 3 and 2. And we do have a value at 5 and 3. Okay, so what it's going to look like. Okay, so that's f of x. Now so I could fit it here. For g of x, we can use the same points actually. We could use 1 and 0, 2 and 1, 4 and 2, 8 and 3. And then in terms of our mapping rule, translated 1 to the right. So same asymptote actually. So x plus 1. And for the y's, negative y plus 5. So a value is negative 1, c value is 5. So that's going to be 2 and 5, 3 and 4, 5 and 3, 9 and 2. Okay, so plotting that, so let's use a different color for this one. 2 and 5. So 2 and 5 would be here. 3 and 4 would be here. 5 and 3, point of intersection, and then 9 and 2 would be here. All right, so interesting looking log function. It has been reflected, but yeah, that's what it's going to look like. So our point of intersection is at 5 and 3 in this case. And there's only one. There's only one point of intersection. Okay, so we can state that here. Therefore, the POI is 5 and 3. All right, well, thank you for watching this video lesson. And yeah, there's some homework questions on solving logarithmic equations, so make sure that you refer to the unit outline for the homework questions.